Okay, so we are continuing the discussion of random processes. So last time we have started random process descriptions, and we are right now again continuing with joint PDF description of random processes. Okay. So for the joint PDF description, now I would like to give a very important example, and this example is Gaussian processes. So Gaussian processes are defined by their joint PDF. I will give the definition immediately. And it's very important type of process because of its practical importance and because of its, let's say, analytical properties and so on. Okay. So let me give the definition. A random process x of t, so this is our notation for now, x with tilde denotes the random process. I'm using different notations because if you examine different textbooks, you will also see different notations. They are all the same actually. It's just a symbol. A random process x of t is called Gaussian process so it's a definition if every n samples of x of t is jointly Gaussian distributed. Jointly Gaussian distributed. Okay. Previously, we have seen the meaning of jointly Gaussian distribution. Okay. So, what's the meaning of that? So, if I have, let's say, n samples, T1, T2, x of Tn, n samples, and their values are x1, x2, x of n, okay. So that is over here, let me write it, x of tk is equal to x of k, okay. Evaluation time is tk, its value is xk. As you see over here. Now the density is as follows. 1 over 2 pi, we have written this before, so I'm just, a little bit faster writing this expression. Cx square root x vector, okay, minus mu x mu x, okay. So that is the definition of joint Gaussian distribution for n random variables, as you see. So what is this x bar? So let's say this mu x bar. X bar is composed of these samples x1, xtn, and I have previously defined them as this is equal to x1, this is equal to xn, okay? So this is the reason that this is just x bar. Its first entry is x1, that is, okay. So what is mu of x? Let me select this one. So this is expected value of this vector. Okay. How do you calculate the expected value of a vector? It's also a vector, as you see, mu x vector, where each entry of this vector is, expectation result of each entry of this vector is included in the mu x definition. Okay. So this is entry-wise expectation. How about the Cx matrix? Well, this is the famous covariance matrix that we have studied long time ago. So CXKL entry of this. Okay, so this is covariance of xk, xl. So this is a kth row, lth column entry of this matrix, as you see over here. Let me write this with blue then. Okay, Cx is this. So this is the definition of joint Gaussians. Okay, jointly Gaussian distributed. As we have discussed before, if you have a single variable, when n, capital N is equal to 1, this becomes standard Gaussian distribution. And this is the definition for if you have more than one random variables which are jointly Gaussian distributed. Sometimes I see some students neglect the importance of this word jointly. Okay. Well, I would like to give an example from Populus. So a brief discussion. Example. Let me write like this. This is not a full example. Example 6.1 from Populus. And Populus is one of our textbooks. You can look it up from syllabus, the version of this textbook. There are several versions of it. So this is 6.1 in that version. Okay. So what do I mean by, or what is the importance of this word jointly? Okay. Now let's assume that now x1, x2 are, let me use capital letters, a different notation. These are random variables. x1, x2 are jointly Gaussian. Okay. So what does that mean? Well, if this is x1, x2, let's say that they are jointly Gaussian and something like this, maybe their level curves are, they're already uncorrelated or independent. Maybe their level curves are something like that. So this is like a peak of this distribution. So its mean is at 0, let's say. Okay. So apart from this peak goes on, there are some tails. And as you see, so this is the peak location at the origin. Well, if mean is equal to 0, one more time, the peak location is over here, and distribution decays as x increases in an exponential manner. It decays very fastly. Now, how about the marginals? Marginal is x1, it's also Gaussian distributed. x2, it's also Gaussian distributed. So Populus's constructive example is this. Now assume that I'm at this location. Okay. So there are some symmetric locations like this. So this distribution has some tails over here. Its peak location is at this point, but it has some tails, passing around this, in this neighborhood. So I'm transferring some of this mass, probability mass, from here. So let me put minus over here. Meaning that the function over here is somewhat like, so there is a function like this, but I'm subtracting only this circular part, the value of this function, a little bit, subtracting, let's say 0.1 inside of this circle. So there is a dip at this point because of this subtraction. And I'm adding this to this part. I'm adding the same amount to this part. So if you calculate the marginal distribution, if you integrate over x2, you cannot sense that because the subtracted part is added over here. So in other words, this is something like this. If I have a one-dimensional Gaussian distribution, again, let's say this is 0 mean. So I'm subtracting this mass. So this is something like this. I'm subtracting this mass over here and adding it over here. Okay, something like that. So your new distribution is also a valid distribution. I do a small amount of subtraction and addition, but clearly this is not Gaussian. Okay. Now, for this one, it's a two-dimensional case. You are subtracting this, so marginal distribution stays the same. Now you can say that, okay, marginal distribution of x1 is staying the same. So at this point, let's say this is x1 star, okay? How about the marginal distribution at x2? So let's see x2 star. Of course it is changing because you have added some mass over here. But here is Populus's constructive example. Populus says that Okay, then over here, minus x1 star. Let's say. Then I'm constructing again. This time I'm subtracting it. So I'm this time doing this. This time I'm adding it. Okay. So this is like this. Let me match the colors. Oh, sorry. Now if you integrate in this direction, if you integrate out x1 when x2 is equal to x2 star, now you don't see a value change because whatever mass you put over here is, you just transfer the same amount of mass from here to there. So what we see is that in this two-dimensional distribution there is a dip, additional dip. There is a lower point over here, dip. There is an additional peak over here. There is an additional dip. There is an additional peak. So this is not a Gaussian distribution anymore. It's something like that. It's like a strange shaped distribution as you see. But what is interesting is that the marginal distributions stays the same because you are adding and subtracting the same mass. Marginal distribution at x1, x1 star, x2 star, they stay the same, okay? So this point is x1 star, x2 star. This is x1 star minus x2 star, okay? So I have this kind of a minus x2 star is over here. So what we see is that if you know that x1 and x2, if you only know x1 and x2 are marginally Gaussian distributed, this does not say anything about their joint distribution, okay? Well, somewhat like an obvious example or obvious statement because it's much more general, but you may think that for the Gaussian distributions we can, do such generalizations. It's not possible as Populus has constructed this example, okay? Very good. So this is the importance of jointly. In some problems you don't see this jointly because it's very difficult to write joint distributions. Joint distribution, as you can appreciate, now you have to explain what is going on between all of these variables, among all of these n variables. It's difficult to express that in practice also. Then you make an assumption and it's not clear whether that assumption is good or not. This example is also related with that. Okay, so we have given this definition, but let me give a random process xt is called Gaussian for if every n samples of x of t is jointly Gaussian distributed. This should be for all n and for all samples. Well, it says every samples, okay? So in other words, for n is equal to 1, I have only x1 distribution. x1 should be Gaussian, but for all t. x2 marginal should be Gaussian, xn marginal should be Gaussian. For n is equal to 2, their pairwise distribution should be Gaussian. Also, as you can imagine, well, this is getting more and more difficult to satisfy all of these conditions, isn't it? But if you know that, for example, these n of them are jointly Gaussian distributed, you can immediately say this is Gaussian, pairwise Gaussian, triplet-wise Gaussian, and so on. You can say such things. Now I would like to give an example on this. Let me keep this and let me erase this part. Populus is a very valuable textbook. It is a little bit difficult to read. But if you want to learn more details of these topics, I highly recommend Populus. It's a classical textbook. Okay? It's right now underappreciated in my opinion. So what's my example? So I'm constructing a random process according to this AT plus B. Okay. So here are the information. Random variables A and B are independent. Okay. A is, let's say n, that means Gaussian, 0 mean, and sigma A square. Okay. B is n, it is, its mean value is, this is a scalar quantity, sigma B square, small b, let's say, something like that. Now the question is, find joint PDF characterization of x of t. Okay. So previously in our earlier example we had something like this: x of t is equal to a cosine 2 pi f t plus a phase. Phase was random, theta was random. Okay. Right now I have two random variables. So how, well, let's write solution, but before writing the solution, please always do this. Try to understand this process. So what kind of process is this? So there's a sample space. From this sample space, I'm constructing lines. Am I right? This is a straight line. So process variable is t. So maybe I have a straight line like that. Maybe I have a straight line like that. Well, different slope, because I don't want them to be parallel. Maybe a straight line like that. So this is called a realization of this process. Let's say this is tau 1, tau 2, etc. Okay? So these are the realizations of this random process. What do I mean by realization? For this one, there's a slope of a1, as you see. There's some slope coming from this distribution. And when t is equal to 0, there is this value is b1. So this is the parameters generating this realization, first realization. Parameters for b is coming from this, parameters for a is coming from that. So this is maybe what we observe. If I make this experiment from the sample space, I observe maybe this line, maybe that line. Okay. So there are probabilities associated with those observations. For example, let me say that this mean value over here is positive. Okay. So what do you expect? If mean value is positive, so I'm expecting this, you know, this is y x of t realizations. Okay. They are realizations. So what do I expect? So I expect something like this. So many straight lines. So it's very ugly looking, but maybe I have something like that. What is the mean? Why do I have such a sketch? The reason is you see that, well, it is more like to have a positive, because this is, you know, y-axis intercept gives me this b value, isn't it? But in these realizations, all of these realizations, b is coming from a positive valued, from a distribution which has a positive valued mean. So what do I expect if I draw such things? I expect that, you know, this is just a drawing, of course, the y-intercept of this x of t lines should be mostly, more probably, on this positive part of this y-axis, because it's more likely. Okay. So this is the way we understand. You know, you draw some, you know, realizations of this random process. Okay. Okay. So what should I do? Now, it says joint PDF description. So here's my comment. Well, first order PDF of x of t. So meaning that I'm evaluating at t1 and I'm calling this a1, x1, sorry. Okay. So I'll be doing this for all t1, of course. So then if I do this, what do I have? This is equal to a times t1 plus b is equal to, now this is my random variable, x1. Okay. So this is random process. Once it is evaluated, it becomes a random variable. So I could have written capital letter for this, but I think, you know, we are clear with this. So what are the other random quantities over here? This and that. So again, this is one function of two random variables. So what do I mean by that? I have two random variables mapped to a single random variable, x1. Okay. This is called one function of two random variables in Populus. Again, Populus's textbook. So what kind of mapping is this? Well, this I think you will immediately agree. This is a linear mapping. Why do I say linear mapping? Because this random variable vector, this is the random vector, is mapped by some, you know, linear weighting. This linear vector, elements of this random vector, is mapped by some weights and summed up to form this random variable. Okay, so it's nothing but a linear combination of two random vectors. Okay. Well, I have such a case. So what do I know? So from the Gaussian information, so if A and B are, the word jointly comes into play, jointly Gaussian, I know that from my previous knowledge, x1 is also Gaussian distributed, Gaussian random variable. Well, the reason is, let me write the reason, since we have studied this before as a fact, since linear combination of jointly Gaussian random variables results in Gaussian random variables. Let me say jointly, because I will use it immediately. Jointly Gaussian after this discussion. Jointly Gaussian random variables. Okay. So is this a linear combination? It's a linear combination. But do we think that A and B are jointly Gaussian distributed? Well, this will coming into play. So let me erase this part. In this example, A and B are jointly Gaussian distributed since F, let's say capital A, capital B, their joint distribution is nothing but FA times FBB, because it says they're independent, okay? So I'm using that independence information over here. So if I multiply this Gaussian density with the variable A, Gaussian density with the variable B, I get their joint density, and this is the joint density when the correlation coefficient is equal to 0. Okay? So if you do this multiplication, you immediately see that indeed the form of this is almost identical to that. Okay? For a 2 by 2 covariance matrix which is only diagonal. Okay? Diagonal covariance matrix. It's very easy to see. So indeed, very happy. Now I can use this information. Then, finally, then x1 is Gaussian random variable. So how do I define x1 then? I need the mean value of x1 and, you know, the variance of x1. That is it. Then expected value of x1 is expected value of A t1 plus b. These are the random quantities. Well, expected value of A is equal to 0. So move t1 out. This is equal to 0. Expected value of b is mu of b. Okay, this is nice. Okay. Then how about this? How can I calculate, you know, the variance, let's say, the variance of x1? Well, they are independent They are uncorrelated Gaussian random variables. Okay. So how do you calculate? We have some examples before. If I have two uncorrelated random variables, their variances, sum of their variances. This is one of the problems that we have solved earlier using two different methods. Okay. Of course, we can calculate this, but right now I'm using my earlier result. So what is the variance of this? A times T1, that is. T1 is constant, it's T1 square times sigma A square plus this is B square, and their covariance should be, covariance of these two random variables should be calculated, but it's equal to 0 because they are independent. Okay, so are we done? We are done. So we see that from here. Let me write a map. So this is N. So this is V and T1 square sigma A square plus sigma B square is the distribution of x1 random variable. Okay. Very good. Of course, this is valid for all T1. Let me write it over here. This is valid for all T1. Okay. If I change T1, this is just a parameter. I see this. Let me keep this because I can make use of it later on. So this is the end of first order PDF description. Now let's see the second order PDF. So my evaluation times are, let's say, x T1, T2. Or let me write this immediately. I'm working with this 2-time instance where the random variables are x1, x2. These T1, T2 is the evaluation time. So I need the density of this. So how can I write this? Well, I will be doing the same. x1 is equal to this. x1 random variable, x2 random variable. Let me copy from this part. This is T1, 1. I have A, B, T2, 1. Okay. x2 is A times T2 plus B by S, something like that. Okay. So now I know that this is also Gaussian vector. Why? This is jointly Gaussian, one more time. If they are jointly Gaussian, their linear processing results in jointly Gaussian random variables. Okay? So this is, let me write jointly, guaranteed to be a jointly Gaussian vector. Meaning that, how nice. I can use this. Why it is so nice? Now I don't have to worry about the density. Density, the shape of the density, or analytical expression of this density is always like this. When you have first order distribution, n is equal to 1, you have a single random variable x1, but this form is always like that. When n is equal to 2, again this matrix becomes 2 by 2, this vector becomes 2 by 1, that is it, that's the only change. So I don't have to worry about, as you see, worry about this expression. Expression is fixed. So what's changing? The parameters of this expression, covariance matrix, and this mean vector is changing. So then let me call this, my x vector, Gaussian vector x. Then what is expected value of x? So this is my x vector. Let me call this, if you wish, a T matrix, a transformation. So this is expected value of T times AB. Okay. T is constant. So this is expected value of AB. So this is the reason that, as you see for Gaussian processes, doing linear operations is so easy. So we have mu B11 vector. So on purpose, I'm trying to make use of matrices. Of course, you can take the expected value of x1, take the expected value of x2, but if you think in terms of matrices, it's a little bit simpler and it's faster. So expectation is on the random vector. What is the expected value of A? It's equal to 0. Expected value of B, this value. Then multiply this by this T matrix. First column is multiplied by 0. Second column is multiplied by, mu B. So mean of this B random variable. Now Cx. So I'm done with this part. So this is my mu x vector for 2 by 1 vector, that is. Okay, because n is equal to 2. So how about my Cx matrix? Cx matrix is a 2 by 2 matrix. So I want to calculate that. But as we have said before, to define this matrix, I need only, well, let me write this, because this is covariance of x1, x1. Covariance of x1, x2. Covariance of x2, x1. x2, x2. Because this is the definition of covariance matrix, as you see. Pairwise covariances are calculated. Now I have to calculate, this one. So how can I calculate that? Let me see. Where's the eraser? So clearly, one more time. This is the random variable at the second evaluation time. This is the random variable at the first evaluation time. I am looking for the covariance calculation. So let me write this then in a generic form. xk, comma, xl. Okay. So this is equal to, so how can I calculate this? So this is by definition expected value of, what is xk? A times tk minus, so plus b, a times tl plus b. Oh, it's not like this. I have to subtract. So how should I, let me write it one more time. So this is x of tk minus, this is a random variable, x of tk, its mean value. So I'm writing the basic definition. TL minus its mean value, XL. Okay. So this is the mean value of this vector, mean value of the other vector. So this is the definition, as you see. Now, how about this part? So if I subtract the means, what do I have? Well, this random variable is a TL plus b. Okay. So let me write this parentheses and this parentheses like this. This is a TL plus b random variable minus the mean of the b random variable. So let me write this plus b0 mean. So this is okay. B0 mean is Zm. This is b random variable minus the mean of the b, mu b. Because as you see, I have the mean value subtracted. Now this is 0 mean random variable. So similarly, a tk plus b 0 mean random variable. Okay. So this is the reason I have discussed this many times. The means are not important. I can always assume the mean value of this bracket is equal to 0 and so on. 0 mean random variable b. I have introduced this. Now I should calculate this kind of a relation. So what do I have? So I see the following. Well, again, 4 terms, 2 plus 2, 4 terms. But let me write the constants, tk, tl over here. Now this is a square is present over here. Since it is zero mean, let me write sigma a square for that. So product of this one with this one. Okay. Now this one with this one. So this is zero mean random variable b square. Then this is plus b square. Okay. Now the cross terms, this and that. But since a and b and also zero mean b, they are independent random variables. This is nothing but, you know, DC constant deterministic value subtracted. And this is zero mean right now. This is also zero mean. Their product is equal to 0. So the cross term, multiplication of this one with this one, after expectation gives you a 0. Okay. Very good. So I'm done with this calculation also. So this is my covariance of xk, xl. Okay. As a double check, covariance is nothing but variance when these two time instances are the same. These two random variables are the same. Then this becomes t1 square sigma a square plus b square. Okay, it's what we have seen earlier. Okay. Now what do I see? I see this vector. This is my mu x vector, and I see this matrix. As you see, this is my Cx 2 by 2 matrix. Once I calculate these two parameters, I insert them over here, and I get my density, second order density. Okay. That is it. So how do I form this matrix? Well, you just write for 1, 1 element, 1, 1, 1, 2 element, 1, 2, something like that. I think you got the idea. Okay. So this is the nice thing about Gaussian distributions. So this form is fixed, but writing, you know, higher order densities, second order, third order, etc., is easy because you're only, you know, changing the dimension of this matrix, changing the dimension of this vector. Okay. That is what we have. So let me write third order description, but okay, this will end with the third order PDF. So we can, I think, a little bit go faster than this. So this is x1, t1, x t2, x t3. These are my 3 random variables. So from here, so how can I describe this? Again, they are jointly Gaussian distributed. Only difference is now I have a third random variable over here, and this is t31, and this is the same mapping. So I need to find this mean vector. So what is this mean vector? Well, mean is always the same. So at all time instance, it is this. Okay. Sometimes we define, later on we will discuss this, if we have, especially for Gaussian distributions, we define, you will see that this is something handy. This is called mean function, especially meaningful for Gaussian. So as you see, the variation of the mean value of this process as a function of t. So this is mean function at t1, mean function at t2, the mean of this. This is the mean function evaluated at t3. So if I tell you the mean function, there is nothing else to do. Okay? How many variables you have is not important. Now what else? I need this 3 by 3 covariance matrix, but, well, do I need to write it one more time? It is this one. Only difference is that I have over here, you know, a third row and third column. It is the same form. So let me write some part of it at least. so on. So I think it's clear what we are doing over here. So it's the same kind of a 3 by 3 matrix. Actually, when you look at this matrix, as we have previously discussed, this is considered as inner product, okay? If this is considered as inner product, then this is the matrix of inner products. If that is the case, this is called the Grameen matrix, okay? This is a higher level, looking at the same calculation. So only thing that I need to completely fill in this matrix entries is use this. So there is nothing else to do. Now there is also a definition, Cx, T1, T2, or Cx, let me say, Ta, Tk, Tl, let's say, Tk, Tl. It will be this. This is sigma A square, Tk, Tl, sigma B square, and guess what this is? This is a covariance function. Okay, this is called covariance function. So for Gaussian distributions, maybe if you know, of the conclusion of this example, after you have seen this example, if you have a Gaussian process, well, define a Gaussian process. If you are interested in the joint density of this Gaussian process, only thing that you need to do is calculate this mean function, calculate this covariance function, and for nth order description, fill in these entries using this mean function, fill in this covariance matrix entries using this covariance function. You are done. Whatever the dimension is, you are done. But the difficult part is you should make sure that you have a Gaussian process. Okay? That is the critical part. Okay, so this is the deal about Gaussians, but I would like to mention, you know, something a little bit, maybe, let me ask a question before mentioning that. Maybe you are also questioning the same fact right now. So the question is, previously, we were writing, do you remember, in the earlier example, let me write a note, remember, in the earlier example, so we were writing the density, let's say joint density, using conditional probabilities, isn't it? We have done a factorization like this, and using this factorization, we have written this joint density because we were able to calculate this. Okay, for the earlier cosine example. Okay, that's a random phase sinusoid. Let's say that example. Okay. Now, how about this one? For this one, we are writing it's for all n. Let's say nth order distribution. We are immediately saying that we can write it like that. But maybe some very careful and attentive students have noticed that I need to take the inverse of this matrix over here. Now the question is, I'm telling you that this is possible to write, very easily and so on. But how do I know that this is invertible? So there is an issue like that. If that is invertible, we are happy. We are done with this. Now I want you to confuse you a little bit. Now let me try to do this, the same kind of reasoning. Remember, this was our conditioning approach. For third order density for this Gaussian process example. You will see immediately. These are my random variables. Now their values. So I will be writing this x conditioned on, let's say, T1, T2. So I have double conditioning. I know both x1 and x2 values. Now the issue is calculation of joint distribution for 3 random variables. So this is conditioning by the first 2. Okay. So I'm trying to get this result one more time, you may say. But let's focus on this part. Okay. So this says that xt1, which is equal to a t1 plus b, is equal to x1, and I know the value of x1. Also says that x2, xt2, a t2 plus b, but I don't know the value of a and b, but I know the value of t1. So I know the left hand side and some parts of right hand side. So can I write this? If I have two observations, as you can imagine, I can find these, a and b random variables. This is given. So for a realization, let's say, there is a realization that I observe. If I observe two values of this random variable, now clearly I can find this a and b uniquely. Okay? Is this clear? Because this matrix is invertible, provided that, sampling times are different. Okay? I have two observations. I can understand the slope and the, DC shift or shift constant of this straight line from here. So what else? Now, if I can solve for AB, now I know the value of AB. This matrix is known. X1, X2 is known. Okay. Now how about X3? X3 is, now let me say that these are my solution. Let me put some stars like this. A star, B star. I have calculated these values. Then X3 is, by definition, A star times T3, this value, plus B star. So do you think this is, it's deterministically found, as you see. So if I have only two observations, then that is sufficient to find any other observation. So what is going on? So this doesn't seem to be Gaussian distributed, isn't it? So this is just a deterministic relation. So this is Gaussian distributed perhaps, but this is not Gaussian distributed anymore. So there is a deterministic relation. So what is this relation? Now this relation is this. X3, so x at T3 given at T1 instant and T2 instant, X3 given X1, X2 is delta, Dirac delta minus A star, I can calculate this from X1, X2, T3 minus B star. So this is not a, Gaussian distribution because it's just an impulse, as you see over here. So the issue is the following. In this case, this covariance matrix, if there is such a deterministic relation, then this covariance matrix will not be invertible. Okay? But still, the main idea is valid, but the covariance matrix becomes degenerate. Okay? This is the reason. So how can I see this, this covariance matrix being not invertible? Well, let me write this Cx, I guess, over here. 3 by 3 case. So this Cx is, let me write some entries of this. First entry, sigma a square T1 square. Next, plus sigma b square. Sigma a square T1 T2 plus sigma b square. T1 T3 plus sigma b square. Okay? Since this is a symmetric matrix, let me write, so this part is equal to this one. Okay? So this is equal to, let me show it like this one. Okay. How about this one? This is sigma a square T2 square plus sigma b square sigma A square T tier square plus sigma B square. This is T2, T3. And this is equal to this. Okay. So what am I doing over here? So I need to express covariance of x3, x3. So that is P3, T3 plus this. I have written it over here for every entry of this matrix. Since it's a symmetric matrix, I'm just writing, you know, upper diagonal part of this matrix because these are the same. I know the symmetry features of this. So can I write this matrix as follows? So here is my observation. Sigma A square T1, T2, T3, T1, T2, T3, okay, plus sigma B square 1, 1, 1, 1, 1, 1. Can I write the same matrix like that? Well, this is looking confusing. I will further explain why we can write it like this, but let me element-wise compare. You see that sigma B square is present at every entry. So this is this part, sigma B square part. So this is all elements of this matrix is 1. So this is this additive part. How about the other part with sigma A square? Sigma A square is a common part. You pull it out. Then you have T1, T2, T2. You have such a structure. Okay? This is, sorry, T2 square. Okay? T2, T1, T2 square, T2, T3, T3, 1, T3, 2, T3 square. Well, if I have a 3 by 3 matrix written in this form. So now let's use our linear algebra skills. What is the rank of this matrix? So if rank is 3, this is invertible. If rank is less than 3, not invertible. So what is the rank of this matrix? So I'm assuming that these sampling times are of course different. I mean, if they are all T1, 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 it's a very dull case. It's not our point. Now, is this clear that the rank of this matrix is just 2? Why? Well, let's think about this way. If the rank is 2 by rank nullity theorem, null space of this matrix should be one-dimensional. So there should be only one vector, at most, and only one vector. There is only one vector, non-trivial one vector. So null space of this matrix should be one-dimensional. Okay? So can you find a vector orthogonal to this and orthogonal to that? Yes, because in three-dimensional space, these are two independent vectors, and there is a third vector which are orthogonal to both of them. So this shows that null space of this matrix is at least one-dimensional. Okay? Can you find any other vector like that? You cannot find any other vector, because these two vectors are independent when T1, T2, well, when two vectors are independent. So this tells us that rank of this matrix is 2. You can say that indeed this is very confusing, because after writing this, how could you, make such an observation and so on. But if you use, this is the reason that I would like to emphasize vector processing. Now, I will use vector processing, and you will get this result immediately. Okay? So let me define my x vector as these samples, and I have T1, T2, T3, 1, 1, 1. Okay? I have A, B defined like this. Okay. Now let's assume that A and B are 0 mean. For now, because as you see, mean does not affect or let me write B0 mean over here. Okay, I think let's assume they are 0 mean. Then Cx is equal to expected value of x transpose, because mean does not affect, as I have said many times before. Now, this is T1, T2, T3. 1, 1, 1. So what is this? Sigma A square, sigma B square. So let me call this T matrix. So this is my T matrix times T1, 1, T2, 1, T3, 1. Okay. This is T1, T2, T3, and I have 1, 1, 1s over here. So what is this? This is T matrix transpose. What is this one? This is the covariance matrix of this vector. Let me call this A vector, let's say. So this is CA. I think it will be clear. Okay. A is a random vector. This random vector has covariance matrix, something like this. Now, what is this result? Because X is equal to T matrix times this A vector, then covariance of X's, T, CA, T transpose. And if you do this calculation, you get this. If you do that calculation carefully, okay? So multiply these two. If you multiply these two matrices first, then you get sigma A square T1, sigma A square T2, sigma A square T3 over here. Okay. Then you have sigma B squares. This multiplies this, I get this, this multiplies this, I get this, okay? So this is the product of these two matrices. Now, I have to calculate, the product of this matrix and this matrix. Do you remember there was a way of calculating? Let me see. Let me erase this part. We are almost done, by the way, but I'm again focusing on some possibly important facts. Now I should multiply this matrix with this matrix, okay? I'm trying to multiply these two this time. So how do you do this? Do you remember we had a method like this? First column multiplied by outer product expansion. And if you do that, first column multiplied by first row, I think you get the idea, okay? Second column multiplied by second row. So there is nothing tricky actually. I have written this covariance matrix. I could have written it at the beginning by this vector processing, but in this example my main purpose is introducing this covariance function, properties of the Gaussian process, and so on. So what we have seen is that if this covariance matrix is degenerate, if it is not invertible, we see an important fact. We see that the elements of that vector, x1, x2, x3, so they are, one element of this vector, let's say, can be expressed as a linear combination of the others, if that is the case, okay? Because there is a dependency and there is a deterministic dependency in linear form, so that tells us that. That becomes a degenerate Gaussian distribution. That is the case when covariance matrices, as I have said, is not invertible. Okay, that is all. We will continue immediately after the break.